Get started. I'm Damon Woods. I work here at the University of Idaho Integrated Design Lab. And part of our work is with the Northwest Energy Efficiency Alliance. They support energy efficiency, and part of that work is energy code trainings. So got Jerry Peterson here, who is an expert in the residential side of things. I'm going to try and dip my toe a little bit into the commercial side of things. Hey, sorry to you. No, it's good to have you here. For those that don't know our lab, we're not an advocacy group. We're just an education group. So we're part of the College of Art and Architecture. And our mission as a group of grad students and research scientists is to really help building professionals like yourselves to build the most efficient, hopefully the most cost-effective buildings out there. And so the Northwest Energy Efficiency Alliance supports us in a number of ways, and one of that is to do research on how effective energy codes are in Idaho and what impacts they have. Jerry here, you've often said a code baseline building is the worst building you can legally build. And that just really sticks with me. And so that's kind of how I'm approaching the lecture today. The code language can be pretty dense. There's about 9 pages devoted just to commercial envelope requirements. And to go through each one piece by piece would bore us all to death. And I won't probably have answers to every detailed question. But what I can do is take notes of any questions that you might have while offering an overview, and hopefully some insight on different code requirements and how to achieve a good building without getting a headache of reading through each paragraph super closely. So what I'll be looking at in terms of requirements is, legally in terms of your building, this is Idaho's current code is the 2018 IECC. There's very few, if any, amendments to the commercial section of the code. There are some amendments on the residential side, but just looking at commercial this morning. So for Idaho buildings, how much heat can escape? What are your insulation requirements? How leaky is it? What are the air tightness requirements? And then how bad are the windows in terms of the fenestration and number of windows you can have where. So for those online, feel free to unmute yourself and ask a question, interrupt me. People here in person do the same. I'd love this to be as interactive as possible. And like I said, I probably can't answer every question, but I can take whatever question you have and take it back and do some digging on it and get an answer back to you. So if our buildings have to be insulated and tight and have adequate windows, how do we actually check for that in the code? In terms of insulation, there's 3 different pathways that they offer. One is to follow ASHRAE 90.1 requirements. That's basically another energy code. The other option is prescriptive. This is probably what most people choose. And there's a couple different ways. There's the R factor method or the U value method, depending on if you're looking at one material or the assembly as a whole. And then third option is performance, where you are modeling the building and then estimating its performance relative to just its a baseline building. So the first pathway is, instead of using 2018 IECC, it references the equivalent 90.1 standard. And that's developed by ASHRAE. It usually lags behind IECC by a couple of years, It's also tends to be a little bit more strict than IECC. But it does offer some flexibility in ways that IECC doesn't. So if you have a building with a lot of semi-heated spaces, 90.1 offers more clarity and more flexibility on some of those semi-heated spaces. So if you're running into headaches of I've got this garage or this equipment shed, and yeah, I've got a few things in it, but it's not being heated to 70 degrees during the wintertime. It's more down to like 50 degrees. 90.1 might be a better compliance option for you in this situation. But you can't just cherry pick. You can't grab some from one code and some from the other code. But if you say, well, in terms of envelope, I'm just going to go with 90.1, you can do that. But you have to, take everything that comes with it. 90.1, it's also more specific on entryways and vestibules. And then there's some flexibility on air leakage. It's also a little more strict in some ways. 90.1 does require inspection and verification of the envelope, something that's not required in 2018 IECC, but will be required in 2021. So if we move forward a code cycle, then it's going to kind of start matching with 90.1. With 90.1, if you do testing, there's a little bit of a grace period there. With 2018 IECC, if you just test for air tightness and it comes back as higher than 0.4 CFM per square foot of the envelope, you just fail. You're going to have to get it retested and make sure that you absolutely pass. Whereas with 90.1, if you test and you fail by just a little bit, but not a lot, if it's between 0.4 and 0.6, then you can make some remediation and do some non-destructive additional testing on it. It can be as simple as a visual inspection of, hey, we sealed up these gaps. You can use an infrared camera or use a smoke pen and look at leakage from a visual way. So you're not necessarily tearing the building apart. So there's a little bit more leeway on the testing option with 90.1. And I kind of like that because it offers some education there. You can see what went wrong during construction and how to fix it. Whereas with 2018, if you just test and you fail, you're really going to have to do a deep dive and make sure that you get below that 0.4 if you're using that testing option. So there's three pathways, right? Pathway one is just switch over to the ASHRAE 90.1. But the language is pretty similar to 2018, so you're not saving a whole lot other than these exceptions that I mentioned here. I'm jumping ahead to pathway 3 before I get to pathway 2, just because I think it's the best way forward. It's using energy modeling to predict energy costs. And the reason that I like this pathway is, yes, it requires energy modeling, but it offers a whole lot more flexibility. You don't have to stick to the window to wall ratios if you do this. You don't have to go through every single material and fenestration and make sure that it's meeting the 2018 IECC requirements. Your air barrier inspection, you don't have to do testing as long as you're still meeting the air tightness requirements. And your model shows that you have 15% lower energy costs than your code baseline building. And energy costs are different than energy use. So that means if you are using natural gas versus electricity for your space heating, that's going to have a really big impact on the performance modeling. So you have to end up doing two different energy models. One where you're just saying, well, this is exactly how leaky I expect my building to be. Here are all the windows. Here's all the equipment that's meeting the legal baseline, the worst building you can legally have, and then compare it to your design. And run it through every hour of the year and make sure it's in the same climate zone, same orientation, and make sure that the energy costs are modeled into this. So that includes, like, Idaho Power, Intermountain Gas tariffs, their time of use, because cost changes between summer and winter. All of that can be baked into the model. But if you show that you are 15% cheaper, which I imagine the client would really like as well, then you can end up getting away from the 9 pages of really detailed material requirements. Yeah, Jerry.
Couple of questions.
Yeah.
Did you just do a simple conversion, BTU to kilowatt, to compare the different power sources?
Well, you would have to go into the model and actually model like an electric boiler versus a gas boiler, and exactly what its efficiency is going to be in situations.
And then what is there a standard modeling, a software that you guys use, or is there multiples? And does it specify which ones it accepts?
It does specify which ones it accepts. It points to the ASHRAE 90.1 again, for which details more. Energy Plus is one, Open Studio, Design Builder, Insight 360. Basically anything that uses a certain type of heat transfer method, and runs an hour-by-hour simulation. So it has to, it's not just this like one design day model. It has to have all of the loads in it and run it hour by hour in that climate zone. That's most energy modeling tools now. And most of the major ones operate with Energy Plus as the engine behind it. They have different front ends. So Open Studio, Insight 360, Cove, BOpt, they all run on Energy Plus as the engine. So they all work. Yeah. Yeah. So if you run with the performance method, you could basically ignore the rest of this presentation. But most people don't. So the other option for envelope is the prescriptive method. And there's two pathways within the prescriptive. This is the R value method or the U factor method. Once again, there's more flexibility if you go with the U factor method than the R value method. The R value method, they give you a table within the code of, you're kind of trying to specify the bats that are going in between the different studs. So it's different depending on the type of building. And it also specifies where you put that insulation. So if you see the little CI, that means continuous insulation. If you see the LS, that means a linear system. It's trying to prevent thermal bridging, right? You've got metal, and if the metal is hitting both the outside and the inside, the heat transfer going through it is going to be enormous. So that's why they have that extra specification of continuous insulation. A mass building would be like CMUs, bricks, that requires continuous insulation. Whereas if you see in the metal building, there's for our climate zone 5, parts of Idaho are climate zone 6, but we're mostly 5. You see the R13 plus R13 CI. So that means you need an R13 bat going in between the metal studs. And in addition to that, you need another R13 continuous that's going either outside or inside of the studs. So it's going across those. And then wood framed is, you've got a couple of different options. Because wood is less conductive than metal, you still have the R13 requirement for in between the studs, but you don't have to do a full R13 continuous insulation. You could do R3.6 continuous, so a pretty thin mat going over those studs. Or you could just put R20 bats in between the studs. that will also need it. The other pathway, instead of specifying the bats and the continuous insulation, where you're just buying, something like this off the shelf, which would have a label of, say, this is it's probably about R13 or so. You can do the U factor method, where you're looking at kind of the whole assembly. And the U values are a little bit more lenient than the R values, because the U values, the U factor, I should say, the total insulation factor accounts for any thermal bridging, right? As opposed to just putting a bat in and saying, okay, we're going to live with the heat transfer through the studs as long as we either have, a lot of insulation for wood studs, or we have a little bit of continuous insulation along the metal studs. The U factor doesn't care your stud spacing. It doesn't care how thick the insulation bat is, as long as the overall wall meets a certain insulation performance. One way you can see whether all the materials that you're specifying for your wall assembly actually meet that U value or U factor is using this construction insulation value calculator. Let me just hop over here. Now I can't see what I'm doing, so never mind. If you go to, actually, let me just spin that for you a little bit. Oh, no, keep passing that. Thank you. And what else? Perfect. You just come over here. Let's see things. So if you go to our website, you should be able to get this tool. Go to services and design tools. We've got this construction insulation value calculator. Oh, that's showing up on the other screen as well. So here you can add in, say, your gypsum, your fiberglass, all of that, and then see the overall wall U factor here. It also has a conversion from IP to SI units. Switch back to the. So just if you have a headache with calculating those, or you're curious about compliance pathways, just know that that's available there. All right, there's a chat. And Dylan has put that link in the chat as well. So thanks, Dylan. There we go. So those are the three major compliance pathways. Just switch over to 90.1, which is pretty similar. Use the performance option where you model the building, or 3, use the R factor U value method where you're actually like layering in all the materials. Exceptions are low energy buildings. And these are buildings with less than 1 watt per square foot, or equipment buildings. Equipment building would be basically a storage shed where you might have mowers, or I thought initially this would work for like a server room or something like that. But there are very specific requirements in terms of it must be less than 500 square feet and have less than 7 watts per square foot of electrical equipment. So if you had a 20 foot by 20 foot building, that would give you the allowance of at 7 watts per square foot, about 5 kilowatts of internal load. But a typical server rack is like 3 to 5 kilowatts. So you'd only have like one server rack in the middle of this 20 by 20 foot room. So probably not best for server racks, but if it's like a garage or a maintenance shed or something like that, and you're only heating it to 50 degrees during the winter time, and you've got less than 5 kilowatts of space heaters, so just a couple little space heaters within the space, then you don't have to do nearly as stringent envelope requirements for walls, roof, etc. You basically just need R5 in climate zone 5 for all the walls and the roof, or R8.3 in climate zone 6. A low energy building would be super, super low energy. There's basically nothing happening within that building, in which case, once again, you could get away with just R5 in those spaces. There are also restrictions on the amount of windows that you can have within the space, because if you look at requirements, insulation requirements for the windows versus the walls, the metal building, remember you had to have R13 bats plus R13 continuous insulation outside of that. So you end up with about an R26 thermal resistance from inside to outside. Whereas with windows, the glass U factor is 0.38, which translates to R3. It's actually lower than that. It's like R2.7 or something like that. So windows, from a heat transfer standpoint, are horrific. But we like to see out. Like, I love the views back here. All the engineers would probably love everybody to be in a foam box, but then we'd all be really depressed. So there's some compromise within the code of trying to encourage fewer poorly performing windows. So according to the 2018 IECC, Idaho's energy code, you can only have 30% of the wall area be windows. There are certain exceptions. You can go up to 40% of window to wall ratio. If it's a 2-story building, at least half of the space inside has to be within a certain distance of the windows. It has to be within a daylighting zone. So for example, for those in person here, pretty much the whole area outside of this room going back down the hallway to the IDL space, that would be considered a daylighting zone because we're next to windows. And so the lights would have to dim. Dylan, let me know if I'm getting anything wrong, since you are the daylighting expert, and talk about what specifically classifies as a daylighting zone. If it's a 3-story building or higher, you can get away with less daylighting zones, so you can have more core and less perimeter space. But that still really limits you. So how does a building like the Arthur, which just went up, which is this huge glass skyscraper, get away with that? They used performance modeling. They must have found some ways to find have efficiency in other areas. Maybe that's their mechanical side. Maybe they're using higher end glass, things like that. So that way they were actually getting just 85% of the energy costs of a conventional building. But that can be challenging to do. And even if you do performance modeling, there's one area that the code will not let you get away with, and that's air tightness. So air tightness is how leaky can your building legally be. In Idaho, for residential in the 2018 IECC, the way they measure it is the air changes per hour that occur when it's pressurized. So you stick a blower door on it. If the whole volume of that air gets exhausted 3 times within 1 hour, then you're meeting. If it's higher than that, then it means you've got extra leaks within the structure that you might need to address. In terms of commercial buildings, it's measured differently. It's measured at the cubic feet per minute per foot squared. So I know the units kind of cancel, but it's how much air, the volume of air that's escaping per the square footage of the exterior surface area. So it's looking at, yeah, the amount of skin that your building has, basically. And that's also at a pressure of 0.3 inches of water gauge, or 75 pascals. And there is this long-standing feeling, instinct, gut response of builders that your house actually needs to breathe, or your building needs to breathe. Otherwise, you might have issues with it. I would really say that is a myth. There's certainly ways to seal a building poorly, but we don't want to just build Swiss cheese structures. People within the building really need to breathe, and we need to provide them with good, clean ventilation air. But the building itself doesn't necessarily need to breathe. Building scientist in Florida, he's got a whole series of blogs on this, as well as a textbook that I'm hoping to use in the building science class here next year, of exactly why people need good ventilation, but buildings should be tight. Looking at just like a house, if your furnace is going and your house is under pressurized, you know, it's trying to pull air from different spaces. And Jerry, you could talk to this even more. Where's that air coming from? If it's just through infiltration, unregulated leaks, that could be pulling through moldy insulation from crawl space. My crawl space is full of dust and mouse droppings and black widows, and I don't want to be like breathing that in all the time. And so having a tight building with balanced ventilation is really what they're trying to go after in terms of why this is within the energy code. And the other thing is it has a huge energy impact. So infiltration as a driver of the loads within a building. In terms of the cooling loads, which is in green, you could see these were different buildings that were tested, kind of neutral over the course of the year. I mean, it feels nice to have a breeze on a summer day, but you don't want that cold draft in the winter, right? And so if your building is leaky, these were just, you know, average buildings that were supposed to be built to code requirements. The infiltration, the drafts coming into the building were driving 30% or more of the heating load. And so if you're trying to reduce gas usage, if you're trying to reduce you know, your electricity consumption in the wintertime, particularly in northern Idaho, at the Vista, they have a winter peak in terms of their utilities, so they're really focused on this. You really want your building to be tighter rather than having essentially windows that are just open in random places in your building that's just pulling in that winter air. So what are the compliance pathways? How does the code say we should tighten up our buildings? Once again, there's prescriptive or performance. The performance is to do testing on the structure itself. So you're pressurizing a part of the building and measuring the air leakage. There's a standard out there for doing that. I don't see this occurring nearly as frequently in commercial buildings as we do in residential buildings, partly because the equipment is larger and more expensive. But Jerry, you were just giving a presentation on home energy ratings and energy rating index, and that requires a blower door test, right, for verification.
On for the tax credit,
yeah,
the Energy Star, yes, those have to be tested.
So testing, I love performance pathways. I love seeing that the building is actually doing what we designed it to, rather than just taking things on faith. But because it's expensive, it's not always done. And so prescriptive is usually the way that architects do go about code compliance in terms of infiltration. So you've got air barriers, looking at materials, assemblies, and fenestration. And even if you do the performance pathway, you still have to have weather sealing in a few different areas in terms of intakes, loading docks, overhead doors have to have weather seals, and you have to have vestibules on your building still. But it doesn't have this lengthy list of 16 different air sealing materials and specifications on windows. Let me see. It's a long section, and it means that as an architect, you have to do your due diligence in making sure that each of the materials that you specify meets these performance requirements. That's kind of laid out within the energy code. So there's a lot of different ways to do air barriers, and you do want to make sure that your air barrier is considered separately from your moisture barrier, because that's where a lot of issues can happen if moisture can't leave the building. And some people have used that as an argument to just, well, we just need to have leaky buildings. But if you have a leaky building, then that's bringing in so much moisture, probably more so in Seattle than in Boise. But that can bring in a lot of extra humidity. And so I still advocate for, and the code does as well, tight air barriers, but well-considered vapor barriers, being careful of where you put those so that the moisture doesn't build up and condense right next to some insulation or something like that and create mold and mildew issues. Other requirements for sealing up the building. If you've got a room with a fuel burning appliance, your boiler, your water heater, that's gas. Either you can have it just outside your building envelope, that's great, or there's a whole bunch of prescriptive methods of here's what you do if it's within your building envelope, and making sure it's sealed and insulated in certain ways in terms of gaskets around the dampers, insulation, at least meeting the below ground requirements in 2018 IECC. It's a little bit different than the rest of the space. And then weather sealing is also required around stairways, recessed lighting, and requirements on vestibules. So that's our current code. I did want to point ahead to what might be coming in 2021/2024, which is also relevant for states outside of Idaho, which have higher energy codes than 2018. One thing that is coming is similar to 90.1. There's going to be basically a certificate of the envelope performance. And I think this is great to actually have a sheet within the construction documents to show here are all the materials and or its overall performance. So that way, when the building transfers owners, the new owner can actually get a sense of how the building performs and what to expect when they open up the walls, rather than it being just some mystery 20 to 40 years down the line. So you need that page, that certificate within there, but it is also going to begin requiring air leakage testing for parts of the building or building types that are considered Group R or residency. So dorms, barracks, hotels, anything that is Group R or Group I institutional. Now there is going to be required air leakage testing. And if you haven't had an envelope consultant or done any of that testing, that could come as a big shock and expense. And so I think it's better to look ahead at that and be on the ball and kind of have your envelope consultant on speed dial now and maybe work through a project or two with them so that you can learn from them, you know, what are they specifically looking for? How are they testing? How can you help them meet this requirement so that your building passes inspection without getting like a nasty surprise, right? Of having never done this to them going to this. The reason they do this specifically for multifamily is, or residential, is because the conventional way that multifamily is air conditioned or ventilated, I think is really unfortunate, where we've got like a lot of trickle vents or construction that happens, and then you've got, you know, air leaks into the space, and if you have uncontrolled leaks into the space, it also can have health impacts, particularly in terms of wildfire smoke, because there's no filtration that's happening if you just have this opening to the outdoors, right? We want people to have good fresh air. I don't think trickle vents or huge gaps underneath the doorways and just blasting everything in from the hallways is the best way to go about it, instead of having like a heat exchanger and some MERV 13 plus filters is going to help in terms of pollen, smoke mitigation, also, you know, viruses and health effects. So that's why they're starting to push the residential harder than they are the commercial in terms of the air leakage testing and requirements there. And so I would just anticipate in future code cycles, if we continue moving down this line, going more and more towards that testing option. So like for buildings in a certain size, it's optional, but it's definitely encouraged in the 2021, and I could see 2027 code, you know, eventually kind of moving that way as well. The other testing that's going to be, or not testing, new code requirement coming out in 2021 is interlocking controls for operable openings. And this would be very relevant if you've got big bays with trucks or equipment, or even just your, you know, your restaurant, your coffee shop, like Push and Pour up on Latah or 10 Barrel here downtown. They've got those big roller doors. You can still have the roller doors, but if they're larger than 40 square feet, then the system has to have some sort of feedback within it so that you're not just air conditioning all of 9th Street. And so within 10 minutes of it being open, the cooling and or heating will shut off, or at least have a very severe setback. Makes sense, but it's an extra set of controls that you just have to be aware of if you do design an envelope that way. In terms of testing and consulting, I pulled this out of this book by Jerica Stacy. There was a study that showed 40% of buildings constructed without an envelope consultant exceeded the leakage requirement. So it was doing worse than it was legally allowed to, but they didn't test it. They just used the prescriptive method of doing things. So they thought, well, we've specified each of the materials, so we should be good. But how those materials all actually fit together when they actually tested it, 40% of them failed. Buildings with envelope consultants all had leakage below 0.25 CFM per square foot. So that's, I can't do math that quickly in my head, but close to 30% improvement over the baseline. And that's just by having somebody look over things present at different stages of construction to check on how all the layers are going together. If you're doing LEED, then LEED points are also available if you do envelope commissioning, and they have different guidelines for how to go about that. So just a heads up in terms of both code compliance and LEED or getting some free LEED points along the way. I think the reason is, once again, it has such a huge impact on the heating energy, particularly in Idaho in our climate zone. So for a commercial building, the first commercial building that produced as much energy as it consumed, it was the 20 Mile South Farm built by City of Boise. And in terms of infiltration, they tried to meet the passive house standard. So they had a target of 0.065 CFM per square foot. And remember that was the current code, if we do the testing, is 0.4. So this is 6 times tighter than Idaho's code. And the way they did that is they did fluid applied, fully adhered air barriers. They taped and sealed all the structural sheathing. And then they also specified super low leakage dampers on all the mechanical equipment so that you don't have air just passing around all those metal pins. Yeah.
Where is this building located?
It's way out west towards Oregon. It's the municipal solid waste facility.
Okay.
So all the solids that come out of our sewage system get trucked out there. And it gets composted essentially. So this is a small area for about 4 employees. They've got some tractors and equipment in there for spreading it around and then just kind of monitoring levels in there. But it's another 10 miles past 10 Mile Road, I think. So
Okay.
yeah,
It's way out there.
it's way out there. Yeah, but it's a cool little building. It does have some solar panels, so that's how they, yeah. And actually, if you go online, the building has its own website, and you can see its power production relative to its use. And since it's been constructed, it's been consistently producing more energy than it's consumed, which is cool. Main takeaways for today. The performance method offers a whole lot more design flexibility. You can kind of skip through a lot of the material specifications and worrying about the ratio of windows on your building. It does require energy modeling, so it's just kind of investing in a separate way of spending your time. But I like it also because it looks at energy costs, which is a very, it's both energy use and energy costs. But if you have clients that are going to be paying the utility bills for the life of that building, particularly like a municipal building, then it makes a lot of sense to try to minimize those costs up front. And by doing so, you get to get away with pages and pages of documentation. Also, the U factor, if you like, nope, can't do performance method on this, don't want to touch energy modeling, fair enough. But between the R value and the U factor, try going with the U factor method because it offers more flexibility in terms of where you're putting your baths and how you're putting your assembly together. And then for the future, be prepared for envelope certificates and or tests on commercial buildings in future code cycles. They're not here in Idaho yet, but I can see the value of them because it has such a huge impact on our heating loads and our heating energy. And so those are my takeaways for today. From that, I'll just open it up to questions. I'm going to leave about 10 minutes for questions.
Sure. Chat for
Yes, you can use ComChat for that.
When does this 2021 IECC code book, when is it expected to hit the streets and be active?
That is a very good question. So the question for those online is, when does the 2021 code become effective in Idaho? I am not, that's up to the Division of Building Safety and their recommendation to the legislature. We'll vote on.
Of course, I was asking for your, like, what do you think?
My opinion off the record. I think we might leapfrog the 2021 and go to the 2024. Which would include basically all the requirements from 2021. Jerry's leaving before I can ask him. When that might happen, it might be up for consideration as early as next year, which wouldn't be adopted for another year or two. That would be I'd say the earliest would be A year from this, from June, so a year from June 2025, so it'd be like June, July 2026 would be the
26, so you're looking at probably realistically 26, 27 timeframe.
yes. Yeah. And I will say traditionally, there's been a lot of back and forth between legislature and Division of Building Safety and the Energy Code Collaborative on residential amendments, but the commercial usually just kind of follows suit. There's usually not a lot of pushback on that. So, yeah.
Thank you.
Yeah. Questions? Anybody online? We've got half a dozen folks online. Okay. Looks like you've signed in, so I can get you AIA credits for that. And I'm also going to be talking with Jerry about ICC accreditation as well. So you should offer that. Yeah. Yeah. All right. There's nothing else. Thanks all.
Off.
I